Hi, I'm Josh, and today I'll be presenting on the mathematics of cities. So I've always just found cities to just be super fascinating places. One, just I love visiting cities and being in them. I find them super cool, but I also find them to be very theoretically interesting. And sort of what I mean by that is I think they have a capacity to show emergent properties in the same way uh, that a beehive as a collection of bees or a brain as a collection of cells might. And I think that because of that, sort of diving into the mathematics could sort of help explain or elucidate some of these properties. So my paper itself has two veins to it, and for the sake of time today, we're only be talking about the first. The first one, which we'll be talking about, is sort of looking at these internal properties of cities and sort of how they emerge from a large collection of people. The latter half of the paper is sort of on the physical structure and geometry of them. Both halves are tied by use of fractal geometry, although in distinct ways. But again, for the sake of time today, we'll only be talking about that first half. So getting into it, you could probably imagine that as the population of a city grows, a lot of things about the city will grow as well. So probably a city with a higher population is going to have more museums, and it'll probably also have more miles of, say, subway lines. What you may or may not expect is that these growth patterns are not necessarily linear, and in fact, work by Louis Betancourt, whose work I will be talking about today and building on, found that these relationships can all be modeled by this power law relationship, where the property is equal to some constant y naught times n, the population raised to some beta. So here a beta greater than 1 would be a superlinear growth, and a beta less than 1 would be a sublinear growth with population. Uh, and here's a chart of some properties in the city. So it's sort of clustered into three groups based on the betas. So properties that are superlinear, so ones that are roughly linear, and ones that are sublinear. So for example, we see that New Patents has a beta of 1.27, which means that, say, a city of population n has X patents per year, then it would not be the case that a city of population 2n has 2x patents, but it would in fact have something closer to 2.4x patents per year, sort of breaking down what this means. And I find this to be super, super cool that we can predict with relatively high accuracy many of these interesting properties, such as new patents produced or gasoline stations in the city, only from the population. I think that's a really cool thing we've done. This is all derived from just observed data. Uh, and I think the more interesting step, though, which we're about to go, is sort of to think about, well, why might these relationships emerge mathematically? And the rest of the presentation today is going to be sort of showing you how we can derive these just by thinking about the properties of cities and such. So what I'll be showing you today is that network volume grows sublinearly with population. Here, network volume is sort of this nebulous concept of just sort of like things that connect people. So networks could be electric lines, it could be pipage, it could be roadways, all of this. Uh, and a lot of the math, again, for the sake of time, is going to be thrown under the hood in this proof. And the reason I'm doing this proof is that sort of the way the structure of the whole proof paper works is that we sort of stack assumptions about cities on top of each other, formalizing them mathematically and proving more and more complex properties about how cities grow with population. And I thought, well, maybe I could just lay out for you all the assumptions we make as a total framework. But I think to give you a better sense of the paper would just be you one small toy example to give you the flavor of what it really looks like and feels like. So to do this, we're going to need two assumptions, the first of which is mixing populations, which basically means that anyone in the city has the resources to get anywhere else in the city. Uh, and to do this, we're going to start by setting the resources per person to y over n equals gn over a. There's some background notation. Y is sort of the total like economic like resources of the city, sort of just this another nebulous concept of resource. So y over n is going to be the resources per person. Here g is a constant derived earlier, which we'll just glaze over for now. N is the population of the city, and a is the area. Then we're going to say that the cost of transversion in the city is equal to epsilon a to the h over d. Here epsilon is the length of some path, or here epsilon is the cost of some path, and a to the h over d is going to be the length of the path, and this derives the cost of traversing the city. Epsilon a to the h over d is equal to epsilon a to the 1/2 in our case, because we're treating d as 2, meaning that we're treating cities as two-dimensional subspaces, and we're setting h, which is a Hausdorff dimension, to 1. Hausdorff dimensions are fractal dimensions, meaning they don't need to be integers, but by the literature, we're choosing h to be 1. And if you're interested in this, you should read my paper, because interesting things happen when we set h to not 1. Then doing some algebra and setting these two equations equal yields this relationship that the area of the city is equal to some constant a times the population to the 2/3. Now we assume incremental network growth, uh, and this just means that sort of the city grows in this decentralized way where everything is connected, and that if someone goes into a vacant space of land, there will be a network that connects them, connecting them everywhere else. And the way we formalize this is just by setting the average infrastructure length per capita, the average distance between individuals, a to the n, a over n to the 1/2. That's what we're going to set the distance to, where a again is the area of the city, n is the population. Uh, well, then from this, we can see that the total network length is going to be L to the n of n equals this quantity dd times the population n equals a to the 1/2 n to the 1/2. But then we can go and plug in the relationship we just derived for the area and population, and plugging that in yields this new equation, L of n to the n. So the total network length of the city is equal to this constant a to the 1/2 times the population to the 5/6. And this is really, really cool, because if we just go back 3 slides and look at this chart, and in the bottom category, we'll see that two prime examples of network length, length of electrical cables and road surface, in real life data have derived betas, or have observed betas of 0.87 and 0.83, which are very, very close to the 5/6 we derived. So you can see that just from a few basic assumptions about how the city works, we can actually derive very good betas that fit with the real world observations. And I think you sort of get a sense now that as we build more and more assumptions, we're going to be able to prove very, very interesting results about how properties of cities grow as population grows. Yeah, thank you very much for your time, and I'll take any questions.